Now, an electric current can produce three important effects. You can see the very important effects due to electric current. These are heating effects, magnetic effects, and chemical effects. Today, we are going to discuss the heating effect of electric current. Now, what happens when an electric current is passing through a high resistance wire, like of a nichrome wire, because nichrome is having very high resistance wire, then the resistance wire becomes very hot and it produces heat, and that is known as heating effect of current. That means if a conductor is purely resistive, having high resistance, the source of energy continuously got dissipated in the form of heat. That means that the source of energy is continuously uh, getting transferred into heat energy. That means in the heating effect of current, transformation of electrical energy into heating energy takes place. Just you have seen that mechanical energy is used to overcome friction, and that is converted into heat. In the same way electrical energy here is converted into heat energy whenever an electric current flows through a high resistance wire. So its role of resistance is here similar to the role of friction in mechanics. Now, the heat production because of the flow of current is known as heating effect of current, and it was given by Joule. That is why it's also known as Joule's law of heating. Now let's try to calculate the formula for the heat produced when an electric current is flowing through a resistance wire. Now see, for instance, you are having a conductor, you are having any resistance wire, and that resistance wire definitely will offer some resistance to the flow of current. That means some work has to be done. Some work must be done by the current continuously to keep itself flowing, right? Because current wants to flow, so current will do some work to keep itself flowing. So let's calculate the work by the current I when it flows through resistance R, and say for instance it's flowing for the time t seconds. Now see, whenever an electric charge moves through a potential difference, we know some amount of work is done, and that work is given by amount of charge flowing multiplied by the potential difference applied. That means W work is equivalent to charge into potential difference, right? And by the definition of current, we know that current is equivalent to charge divided by time. And if we see what is the value of charge here, that is equal to current into time. So we'll get Q I into T. So let's substitute this Q in this equation. So W as it is, for Q we will substitute I into T and then V. So here W is equal to potential difference into current into time, right? Now for a steady current, heat produced in time t is equal to V into I. Now I'm saying heat produced is equal to V into I into T, because here it is W, work is equivalent to V into I into T. But we know that the work done or the electrical energy consumed is converted into heat energy. Whether it is the work done or it is the electrical energy consumed, that is all the work done, all the electrical energy consumed is converted into heat by the appliance, right? Because whatever work is done, whatever electrical energy an appliance consumes, that all of the energy, that all of the work is getting converted into heat energy. So we can replace W by heat. So we have written here, instead of W, it's heat. So heat produced is equivalent to V into I into T. Now, as per Ohm's law, we know that potential difference is equivalent to current into resistance. So we can substitute IR for the value of V. So H as it is, for V, we will write I into R and then I into T. Now, I into I will be square of I, and then R into T is as it is. That means heat produced is equal to I square into R into T joules. That is, this much of heat energy is produced when current I is flowing through a circuit of having resistance of say R ohms, and when current is flowing for T seconds. So that means heating effect is equal to the square of current into resistance of wire into time for which current is passed. From this relation, you can observe that heat produced is directly proportional to the current. That means heat is directly proportional to the square of current, as we have seen in this formula, right? And heat produced is directly proportional to the resistance for a given current. Again, heat produced is directly proportional to the resistance. What do we mean by directly proportional? It means if current here increases, current, suppose if we double the current here, heat will get, heat will increase 4 times. Okay, if we have the current here, heat generated will become one fourth, because it is square of current. Okay, and here heat is directly proportional to resistance. That means if we double the resistance, heat produced will also get doubled. If we halve the resistance, heat produced will also be halved. Okay, so that means more resistance will offer more, will produce more heat, and the wire having low resistance will produce low resistance. We can observe this from the relation of H is directly proportional to resistance. Next, heat produced is directly proportional to the time for which the current flows through the resistor. Again, that means if you are using an appliance for more time, then definitely heat produced will be more. And if you are using the appliance for less amount of time, then the heat produced will be less. If it means double the time, double the heat produced, half the time, half will be the heat produced. So Joules' law of heating says that whenever current flows through a resistance wire, current electrical energy gets converted into heat energy. That means a lot of heat is produced, and that heat produced is equal to square of current multiplied by resistance multiplied by time. Now, all the appliances which run on electricity do not convert all the electrical energy into heat energy. Only the electrical heating appliances convert most of the electrical energy into heat energy. For instance, when current passes through an electrical appliance, say fan, then most of the electrical energy is used up in running the fan, in turning the fan. That means only very small amount of electrical energy gets converted into heat energy by fan. So we due to this, what happens, small amount of heat energy is released. That is why electric fan becomes slightly warm when run continuously for a long time. But on the other hand, if current is passing through some electrical heating appliances, say suppose electric heater, electric kettle, then what happens, most of the electrical energy is converted into heat. And all the heating appliances have some heating element, or you can say have some heating coil, and that coil, that element is made of very high resistance wire, like nichrome wire, which helps them to convert most of the electrical energy into heat energy. So the Joules law has many applications in our day-to-day life, as this heating effect is utilized in the working of electrical heating appliances like iron, electric kettle, electric toaster, electric oven, water heaters, room heaters. So in all these heating appliances, these contain a coil of high resistance wire, usually made of nichrome alloy. And when these appliances are connected to the power supply by insulated copper wires, then large amount of heat is produced in these heating coils. Why? Because they are having very high resistance. But a negligible heat is produced in the connecting wires. That is a wire which is connecting them, copper wire. That there negligible amount of heat is produced, because actually heat is produced in the heating element. That means in the coil, in the nichrome which is present inside. Okay. So let us see the application of this heating current in the case of bulb. So we know that we utilize electrical bulbs, electric lamps for producing light, right? So whenever electric current passes through a very thin, high resistance filament. Now in the bulb we are having a filament that is made of tungsten. Okay, so this tungsten is having a very high melting point of 3380 degrees Celsius, and it is having very high resistance. Now, whenever current passes through this thin, high resistance filament, tungsten filament becomes very hot. This tungsten becomes very white hot actually, and due to which it emits light. But yes, that same current which is flowing through this filament also produces enormous heat. Even most of the energy consumed by the appliance appears as heat, and a small amount is converted into life. So that means enormous amount of heat is produced because of this filament. And now how this filament produces that amount of heat? Because this filament is having very high melting point, and because it is having very high resistance. Now, because of its very high melting point, what happens? This tungsten gets very hot, even white hot, without melting, because its melting point is very high. It has other properties also, like it's having high flexibility. It has low rate of evaporation at high temperature. So basically, this becomes white hot and glows to emit light. And at that time, its temperature is almost 2500 degrees Celsius. That means it can't get melted because of its high melting point, right? And one more thing, inside this bulb we are having a chemically unreactive gas. Like we can have a gas of argon, we can have a gas of nitrogen, or mixture of both. Now, why the bulb is filled with this kind of unreactive gas? Because what happens if air is present in the bulb, then definitely this extremely hot tungsten would burn up quickly in the oxygen. So that is why this bulb is filled with the unreactive gas, because these unreactive gases, they do not react with hot tungsten, and which prolongs the life of the filaments of the electric lamps. So see, this is a one kind of application of Joules law of heating, or you can say Joules heating effect, which we use in our day-to-day life. And yeah, these type of lamps are not power efficient filament type lamps. So that is why these days tube lights are used, because they are much more efficient and they are having no filaments. Now let's look at the another application. The most important application, that is the heating effect, is utilized in the electric fuse. Now this electric fuse is a kind of a device which protects circuits and appliances by stopping flow of electric current in case of short circuit or overloading. That means this fuse is a kind of a safety device. It protects our household wiring, our appliances. Now, what is this fuse made of? You can see it's here a short type of a wire. Basically, it's a short length of a wire, and that wire is actually made of metals or um, alloys, you can say, and alloys of like tin, copper, aluminum. And normally, usually, what happens? Tin plated copper wire is used in fuses, and these fuse will have a low melting point, will have high resistance, and they are always connected in series. They are having high resistance than the rest of the wiring in a house. So whenever current in the house hold electric circuits rises too much because of anything, because of some reason, whenever when the current in electric circuits rises too much, this fuse wire, because it's having low melting point, so that is what happens, this fuse wire gets melted, and because of its melting, circuit gets broken up. It means it will break the circuit after melting, and due to which current will stop flowing, and this prevents the fire in house. Because if the large amount of current will flow inside the wires of house due to overheating, maybe a fire will broke out, maybe some damage will happen to our appliances. But because of its low melting point, it melts away and breaks the circuit, due to which current stops flowing, and it prevents our appliances from the damage due to excessive current flowing through them. So this electric fuse is a very important application of the heating effect of current.